Thanks, Guillermo. So as Guillermo said, and I do have a hardware background, so I'm going to talk about the fact that we need to go all the way from algorithms to hardware to really make a difference. Deep learning certainly has made a huge amount of progress, and we all know that. We are in this conference here, both in vision and in language models and so on. So if I were to really look at, and this is some of the data that you might have seen before, if I were to really look at the power consumption, the computation required for training, and I'm showing here as an example, NAS for large-scale NAS, you probably need, for example, computations of the order of 10 to the 21 or so. So that's a humongous number of computations that you need, and if you really translate that into common carbon footprint, the numbers are quite outrageous. Turns out it's equivalent to taking a round trip, a flight from San Francisco to New York, and it's much more than that. On the other side of it, if we were to really look at edge applications, and in particular actually looked at smart glass and a Google Edge TPU, and we did some analysis of implementing a RetinaNet DNN, and then calculated the battery life under ideal conditions. We didn't even consider the cost for display and so on, which is going to require a good amount of power consumption. It turns out that the battery life under ideal conditions is about an hour. So with all the non-idealities, display and other things that's going to come into picture, it's probably going to be half an hour or so. So the question, of course, is where do these inefficiencies come from? We certainly know the brain is reasonably efficient, and we have an existential proof of that. These inefficiencies come from the fact that we possibly don't have the right kind of algorithms, we don't have the right kind of sensors and the hardware architecture, and finally, at the end of it, at the bottom of it, we probably don't have the right kind of circuits and devices. So if I were to now really think about comparing with the biological systems, and the biological systems do possess a level of functionality that is unmatched with the artificial systems. And this is an example that we considered, which is a fruit fly, which has about 100,000 neurons. They fly fast, avoiding obstacles and dodge dynamic obstacles really efficiently. And then working with Kostas here, we actually figured out that the system that they implemented, the flying monkey, the compute power is about 1 to 2 watts, the compute power. Where on the other side of it, if you really look at the fruit fly, it's probably about microwatts of power consumption. So there's a huge amount of efficiency gap that exists. So the question, of course, is can we try to reduce that efficiency gap in some ways? So the big picture that we looked at is it possible to actually have autonomous intelligent systems by improving the compute efficiency and the robustness of these cognitive systems through a cross-layer approach, going all the way from algorithms to hardware. And we'll find out that there's a need for really thinking about co-designing the algorithms of the hardware in some ways. So the exemplary application driver that we looked at as a part of an IARPA project that Kostas is involved in, and also as a part of the Center for Brain-Inspired Computing, which is a center funded by DARPA and SRC companies. We're looking at basically vision-based navigation, completely vision-based navigation. And the idea is to really do localization, mapping, odometry, path planning, and so on, where, with the diverse learning modalities, supervised learning, reinforcement learning, and also looked at different kinds of, spike-based and non-spike-based computing to get a compute efficiency which is more than 100x better than what can be done today. I kept robustness here. Whatever the design that we do at the end of it, they certainly need to be robust. And sometimes it's a little bit difficult to define and to really say, hey, how much of an improvement in robustness that we want, but the robustness and explainability certainly are important issues. So, as I said, in order to really handle this problem, we need to take a cross-layer design approach. And in the context of this workshop, we're going to be looking at sensors going from different kinds of cameras, in particular, actually the frame-based cameras and the DVS cameras, looking at the algorithms and the hardware. So now, if I were to really go from point A to point B, for this drone to go from point A to point B, avoiding obstacles, you've got to do an optical flow segmentation, object detection, you name it, tracking, localization, and so on. So to start with, what kind of sensors are we going to use? And in this particular case, we're going to be looking at only frame-based and event-based cameras. And the algorithms that we need to develop, and I'll go very, very briefly into some of those, is that you have to do these optical flow segmentation, blah, 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 and what kind of network architecture is going to be suitable for that. And that turns out to be quite important. And we'll see that hybrid in some ways is the way to go, and I'll talk about that. And finally, at the end of it, the algorithms that we develop has to be implemented in the right kind of hardware. And in some ways, today's hardwares are basically the CPUs and the TPUs and the GPUs. And so question, of course, is if you were to implement some of those in these today's hardware, do you have the efficiency? And if you don't, what are the things that we really need to do to actually come up with the right kind of hardware? So just to very quickly go over the different kind of modalities that one has to look at, because we're looking at different kind of cameras, and the kind of application that we're looking at are, so to say, sequential applications. Turns out that the network architecture, certainly one can look at the standard deep learning networks, but for sequential tasks, in a lot of ways, turns out, and especially for these DVS cameras with spike inputs, it does make sense to use the spike-based computation units. And the spiking networks, what are spiking networks? They're basically, if you think about it, there are RNNs. And there's an inherent recurrence because of the fact that you have a membrane potential, which can be a leaky integrated fire kind of neuron. And on the other side of it, it's difficult to train in a lot of ways. So is it possible that I actually come up with some hybrid networks where part of the network could be leaky integrated and fire kind of neurons, other part of the network could potentially be ReLU kind of activation that you have. And it turns out for such networks you can potentially get a good amount of improvement, both in energy and in terms of accuracy. Now, the hardware computational efficiency, as I mentioned, currently we do use GPUs, and we'll see that some of these algorithms that we implemented in the GPUs may not be quite efficient. So there's a need to really think about new hardware. There's a huge amount of focus today on really looking at compute in memory kind of hardwares. Why compute in memory? The interesting thing is that today's hardware, if you really look at it, the von Neumann kind of architecture, you actually, if you were to do, for example, a huge number of matrix vector multiplication, and that's what you end up doing in all these in algorithms, turns out that the traffic from the memory to the CPU can be quite huge. So is it possible that I do the computations in the memory itself in some ways and thereby reduce that traffic if I can, and that can potentially give you a large amount of improvements? Sparsity is another thing that plays a big role in deep learning, and so if I can actually effectively utilize sparsity in my architecture, then I can also get a good amount of improvement. And finally, at the end of it, you find that most of these hardware that we're looking at are not quite suitable for SNNs. They don't do event-driven computation, and they may not effectively implement some of these algorithms. So there's a need to really think about the hardware architecture that's suitable for that. There are non-commercial hardwares available. For example, the Intel Loihi. They may not today be able to implement large-scale designs, but they can potentially be quite effective for a class of applications. And certainly, I'm not going to go into any details of it. There are some interesting, emerging devices that can potentially be used, which can mimic the neuron and the synaptic functionalities in a more efficient way. And finally, the training complexity. I'm not going to go into any details of that, but is it important in a lot of applications that I do? On-chip learning, can I do that effectively? So with that in mind, I'm just going to briefly talk about some of these sensors that one can use, and in particular, actually the DVS and the frame-based cameras. Again, I'm probably talking to the coir here, and you're all familiar with it. But what is really important to understand that the choice of the sensors would dictate the choice of the different modalities. How much memory requirement that I'm going to have, what the kind of latency I'm going to have, and the energy and accuracy. That's going to play a role. So again, the frame-based cameras are the regular cameras on the other side of it. You can potentially think of these DVS cameras where when there's a relative motion between the object and the camera, then you actually have a spike which is formed. And if you can effectively use those spikes for computation, that can be quite exciting. I'm going to quickly go over, and one other thing I just wanted to mention is the fact that when it comes to these event-based cameras, since you end up having spikes as input, turns out that the spike-based computation units, like a spiking neural network, which are again effectively an RNN or a kind of a low-cost version of an LSTM, if I may say so, can be potentially useful and for these sequential tasks. So now if I go into the algorithm side of things, what it really tells you is that if I have these sensor inputs that are coming in, is it possible that I actually have the right kind of network architecture, the right kind of training technique to do, for example, optical flow segmentations and so on. So if I have to really look at optical flow, and this is an example, I'm going to very quickly go over it. We looked at the possibility of using both the cameras, the event camera input and the frame camera input, combine them together, fuse them together into a network, so to say, take the best of both worlds in some ways and do optical flow. And it turns out that actually the fusion flow net that we presented, I think, at ICRA last year, actually gives you quite good results compared to, for example, a network which is completely spiking. It was actually a little bit difficult to train from that angle, but even though the spiking network actually had less number of slightly less parameters, it turns out actually the fusion flow net gave much better results in terms of the endpoint error. And finally, we looked at very, very low complexity network architectures, like a completely spiking network architecture with about 60,000 parameters, where these other ones are actually about 10 million parameters or so. And it turns out actually can do reasonably well. And the reason why it does reasonably well is because of the fact that it can effectively utilize the membrane potential, or in other words, effectively use it as an RNN for these flows. And these are some of the results of this spike flow net, fusion flow net, and this full-fledged ANN. And it turns out that fusion flow net, as I mentioned, does probably the best job. And I wanted to mention a few other things. We looked at very low complexity, lightweight networks like a spiking network, and then tried to analyze these low complexity spiking networks with the corresponding ANN. And it turns out that the corresponding ANN would require larger number of parameters. And the reason why it would require a larger number of parameters is because of the fact that, effectively, again, we're utilizing an SNN to do work as an LSTM or an RNN. And what we found is that these low complexity networks can potentially give you the same kind of power consumption, rather same kind of accuracy as the baseline ANN that I'm showing there, however with a lot lower number of parameters and at the end of it, lot lower power consumption. I know that don't have time with doing other kinds of things that we did in object detection, segmentations and all, but just wanted to mention that, again, the hybrid approach of really taking both inputs of the DVS camera and the hybrid networks actually does give you, good segmentation results. Finally, in object detection and tracking, one of the things that we looked at, and this was presented at this year's ICRA, is the fact that you can use completely low complexity spike-based computation unit to be able to actually do a tracking of these objects. To that effect, this is a very, very simple one-layer spiking network that I'm showing using DVS camera inputs, and to be able to actually not only track the objects, but at the same time be able to say what speed it's going at. And this is an example of that. I think there's a demo in one of the sessions today where showing that it's possible to actually use these these DVS cameras again to do, for example, not only, let me see if I can move it faster. Instead of that, I messed it up. Yeah, so what it really does is that you can see the different colored, and this ball was moving, and depending on the speed, we can actually detect what speed it's going at low speed, high speed, medium speed, and so on, with a very, very simple mind. It's spike-based computation unit. And I wanted to also show, for example, the one that Kostas has been looking at as a part of our project is really this EV catcher, which is taking inspiration from nature and trying to able to catch the ball. Again, the camera being the DPS camera. Finally, very quickly talk about, so since we talk about these hybrid architectures, network architectures, what kind of hardware architecture is going to be suitable for implementing some of these algorithms. And these, it's not that you're building an ASIC, you're building an accelerator, right? And at the end of it, it has to have a good amount of programmability. So the hardware architecture that one has to efficiently implement the algorithms, both the SNNs and ANNs, and we believe that there's a need for these hybrid systems. And finally, another thing that I mentioned earlier is the fact that there's a need to really think about in-memory computing in some ways to be able to actually do this matrix vector multiplication very effectively. If you have to do, for example, transcendental functions in some of these transformer-like architectures, it turns out it's also possible to actually embed sometimes a ROM into a RAM and to be able to do some of these transcendental functions more efficiently, rather than storing it in a math table in your DRAM. So is it possible that I do in-memory, near and in-memory computing? There are other possibilities. You can actually do, approximate stochastic hardware and so on. I'm not going to go into that, but if I'm able to do in-memory computing, and it turns out, then I can actually get potentially, compared to what's there today, GPUs and CPUs, you can get a good amount of improvement in both energy consumption and power. So the basic idea, again, I probably don't have much time, but the basic idea is to really think about having a crossbar. And a crossbar is really nothing other than having a resistive element at the cross point of each of these, at the crossbars. And if you have inputs which are coming in, which are voltage, the output is going to be current, which is a summation of VI times GI. Or in other words, it's actually a dot product that you end up doing. Now, if you do this dot product, it's an analog domain. There's a lot of other things that you have to do. You have to transform that into a digital domain, and you have to use the right kind of devices. It's not that you can't do CMOS, but you can potentially use these other kinds of devices, and you can think of an architecture where you have these different kinds of crossbars put together with some peripheral circuitry, which in this particular case are going to be the analog to digital converters. And if you do that, you can potentially think of a spatial architecture which is highly parallel and can implement some of these algorithms very efficiently. Now if I take CMOS as an example, what we did is we looked at different kinds of implementation, to start with the baseline being a GPU-based baseline, which in this particular case is an NVIDIA Jetson TX2 for comparison. And then we actually build our own. We developed an adaptive sparsity-aware compute-in-memory architecture for ANNs. And then we also developed a spiking neural network accelerator. The spiking neural network becomes a little bit different because your membrane potential has to be stored. So if you're doing in-memory computing, in that case, you have to not only think about the weights, but you have to also think about, how to store that membrane potential and effectively update it. And again, doing in-memory computing. And then also looked at some of these, emerging hardware techniques and using some of those to get rid of this ADC, which can be the analog to digital networks, which is the bottleneck. And finally, also ended up using some comparisons with Intel Loihi processor. Just to give you an idea, the hardware architecture on the Jetson 2, where we actually implemented this, optical flow prediction. And what I wanted to underscore is the fact that even though this is an all-ANN implementation, which actually shows the energy consumption on this axis on an implementation in the Jetson. So this is all ANN. This is a hybrid network, SNN and ANN, and this is all SNN, which has a huge, really low number of parameters. But what you really end up seeing is that the power consumption for these ANNs, SNNs are quite higher than these large-scale ANNs that we implemented. That really says that it's actually not quite suitable for the kind of implementations that we're looking at. So what we did is we actually implemented an hardware accelerator doing in-memory computing. And again, this chip, I'm not going to go into the details of it. It's actually a CMOS chip, which we implemented, showing that, hey, it's possible to get a good amount of TOPS per watt, and the energy consumption is really good, but it still actually has a power consumption which is dominated which is shown in this orange by the analog to digital converters. So if I can get rid of these analog to digital converters, then we can potentially get a large amount of improvement. And to that effect, actually, we looked at some of those. But before that, I also wanted to mention that, looked at a spike-based computation unit. And if you can use a spike-based computation, you need to do the computation. And again, remember, as I mentioned earlier, that it's kind of like an LSTM that you're using. A few things which are important is that you need to really look at sequential tasks. A lot of times we were actually earlier implementing, for example, just for images using standard images using SNNs, it may not be suitable. But if you do for the sequential task, it does make sense to use SNNs. And as I mentioned, that one has to really think about the membrane potential along with the parameters that you have to do for in-memory computing. So that's what we did. And what we really did here is that we came up with an architecture which has a fused weight memory and the membrane potential memory together to do these computations. And what it really shows is that, and then this is a chip that we implemented in a 65 nanometer technology, that one can get potentially a large improvement compared to the ANNs. Remember that I showed earlier that the Jetson is not able to do that. Now you're able to get a good amount of improvement over the ANNs. And quickly mentioning the fact that power consumption was dominated by the analog to digital converters, but if you now are able to actually think about getting rid of these analog to digital converters, you might say, hey, what's going to happen? My accuracy is going to decrease. Yes, if you don't do anything, the accuracy is going to decrease. But if you can train on the hardware, meaning thereby that not only you learn the data, you also learn the hardware at the same time. So if you do that, in that case, you can show that you can get a good amount of improvement compared to the ADC-based designs, and that turns out to be quite interesting. And this is actually an example showing that completely ADC-based implementations of and doing ADC-less training with full precision, and this one, and the AE results, which is the endpoint error that we have, are slightly worse, but certainly acceptable in a lot of these cases. I'm not going to talk about Intel Loihi implementation, but actually in one of the posters, they're going to talk about that tracking that we did on the Loihi, and Loihi does well, but certainly not implement large-scale designs. So key takeaways, the way I look at it, proper sensor fusion, proper hybrid networks, taking really the best of both worlds in some ways, and can potentially capture the essence of some of these training, and in some cases for completely sequential applications we can use SNNs, and again SNNs should be used in a way that it's suitable for use in proper applications. So that is important, not for images but really for sequential tasks. And we don't really have, one of the things that we don't have is sort of the next generation data sets. I know that Kostas has been working on some of those, and we actually looked at some of those, but development of some of these synthetic and real world data sets is going to be really important to really keep this moving. And finally, from the hardware point of view, again, I feel that proper hardware architectures are going to be essential to reap the benefits of what we talked about. And again, hybrid in a lot of ways I feel is the way to go. Okay? Thank you.